So in the last lecture, we are discussing about the various design VLSI design styles. Mainly, we have discussed that programmable logic devices, and the important design technology is now field programmable gate array or the FPGA. So the design flow of FPGA is same what we have discussed. The design entry, what we have discussed, that design entry should be in different form, the behavioral, structural. So here mainly this thing is in some HDL code. So it is in some schematic form, or some HDL language like VHDL or Verilog. And normally the FPGAs available, or the FPGA vendors, are Synopsys, and the most important normally the people use is the ALDEC, that is actually the Xilinx foundations. This is for Xilinx, and implementation includes the placement and routing. Another thing is that bit stream generation using Xilinx M1 technology. Normally people use the nowadays use Xilinx FPGA. So the basic characteristics of FPGA. The CLB means that configurable logic blocks. CLBs are combinational as well as sequential. Normally the sequential blocks are synthesized by flip-flops. A matrix of programmable interconnects surrounds the basic cells. Last day we have seen the picture, the basic programmable IO cells surround the core. None of the mask layers are customized. Customized means just you can think that this is some tailored or not tailored. That means based on the designer's requirement, whether things are programmed or already they are predefined. So, this is it is here all the things are predefined, that logic blocks as well as that interconnections, only the designers are programming or that controlling the IOs as well as that logics, that means interconnects and logics. So, this point is very important, that none of the mask layers are customized. Now, a method for programming is needed for the basic cells as well as the interconnects. Now, another FPGA family is that is called the Altera. I am telling mainly the logic elements used in that Altera family. So, here the LEs means logic elements are 4 input lookup tables plus 1 flip flop and large blocks of SRAM. Now, there are two varieties, there are two types. One is Altera Max. This is mainly the EEPROM based. Another is Altera Flex. And this is of normal type, that means logic elements are lookup tables and the simple SRAM memories are there. So, this is of normal type. So, nowadays these FPGAs are very important because of its fast prototyping, because what we have discussed, that a array, two-dimensional array of CLBs are there and that interconnects are there, and people only what the designer do, the designers based on their requirement they only program that thing. So, the manufacturing time, that is, or sometimes we call the design turnaround time, is only few hours, and that is why almost all over the world now the FPGA design style is the number one, particularly for the academics and the small industries, that they are using that FPGAs. So, that hardware that is available, everything is fixed, that is not customized, I have told, and only that we are programming that thing. Not only it is not reprogrammable, that is only for one that is burnt and that application is there. Now, the second category is the GATOR. So, here also that The difference from that FPGA is that FPGA is that mainly the chip is designed with the user programming. Just now what I have told, that one programming style is there. Mainly this is provided by the FPGA vendors. But here that gate array is that a array of basic cells, predefined basic cells are there, and interconnections are mainly done by using some metals, that means some mask. So this is the difference. I am giving the design implementation. So gate arrays, design implementation is done with metal mask design. It requires two-step implementation process. The first one is that based on generic, or sometimes you call that standard masks of transistors. Second one, the metal interconnects. Which connects the array of transistors. Now, these GAs are of mainly of two types. These gate arrays, normally they are of two types. One is called that channeled one, second one is the channelless, or sometimes it is called channel free. Now first we see the channel GA. So this is one base cell. See here, this is the array of base cells. So this is one. So this is one base cell, and this is the channel. This is some predefined space kept for the interconnections or the interconnecting the base cells. Now the characteristics are only the interconnects are customized, because the array of base cells are fixed. Worst case, these base cells are transistors. So only the interconnects are customized. interconnects use the predefined spaces between rows of base cells. At the design time, or sometimes it is called manufacturing lead time, design time is slightly higher than that of FPGAs. It is 2 days to 2 weeks. But one thing is that it is much more flexible, as the basic cells can be of transistors. There it was some configurable logic blocks are there. So here that can be some cells or some transistors. So channelless GS, again if we see one basic cell, so here there is no channel for interconnections. Here all these are basic cells, and normally some top layers, a few top layers are kept, that is the metal layers for interconnections. That is why here the density is much higher than that of channeled one. So these are basic cells. So only some of the mask layers are customized. That is why sometimes they are called masked GA, masked gate array, MGS. Normally in practically it is called that, in the market it is called that masked GS. It is masked gate array. And the design turnaround time is almost same, the 2 days to 2 weeks. Now that what is the basic feature of that or advantages over FPGA? The GA, chip utilization factor, what does it mean, that chip utilization factor? Remember that in FPGA that only some CLBs are there and some switch boxes are also there at each junction for that programmable interconnections. Here it is only for channeled this is only for interconnection and some basic cells or some transistors, and for channelless this is only for basic cells and some two or three metal layers are kept for interconnections. That is, the density is much higher than that of FPGA, and that is called the chip utilization factor. Sometimes it is called chip area divided by the total chip area, used chip area divided by the total chip area, just like the definition of throughput. Okay. So, utilization. Now, chip speed is also higher. This is mainly for because here the basic element is transistor, not that upper level modules. There the CLBs are truth tables, and all of we know that if we want to access some memory, always that is a slow. So, lookup tables. So, if we give that input, then what will be the output that I am accessing from some memory, because they are the main elements were that RAMs. Here the main element is transistor or some cells consisting of a few transistors. So, that is why the speed is higher. Current GATOR chips, the GA chips can implement hundreds of thousands this should be or thousands of logic gates. So, if we want some fast design, that gate array is advantageous than that of FPGAs. Now, these are that programmable type. Though it is a we are categorized that gate array is a different type of programmable logic devices, but almost the concept is same. There are some predefined cells and some predefined interconnection paths or some customized paths for that interconnection of that basic cells. So, that can be a transistor, that can be upper level connections. Now, another type of approach is that cell based design, the standard cell based design. Currently, this is for that huge complexity of VLSI, that means huge number of transistors to be used in one IC, that standard cell based design is the most advantageous one. So, we can tell that thing that standard cell based design. Now, the basic idea is, say, some predefined pre-characterized gates or cells are already in my library, and these which are commonly used, say we are telling some commonly used gates you can tell these are some logic cells also. Designed and tested. These are, say, some NAND gates, NOR gates, some AND OR inverter, this is some cell, OAI, that OR and inverter, some delatch, some flip-flops. So this is some 2 input AND, another 2 input OR, one inverter. Say it has been observed that this type of cells or this type of logic blocks are commonly used in one design. So it is designed and characterized as a cell and it is kept in the library. This is called, say, some AOI cell. Sometimes it is called that semi-custom design, because already these blocks or that basic elements or basic cells that are tested, designed, tested, and it is kept in the library, and based on our application we are just collecting from the library. Now that the basic element is the inverter in its standard cell type of thing. Now this is of, say, some standard size transistors. So one inverter can be of these 3 different types, or it can be other types also. What the designer will do, say he is doing some phase lock loop circuit, PLL circuit. Then for some parts it wants that delay should be more. Not always it is the we want that the transistor inverter should be fast or the design should be fast. Sometimes we want to put a delay. So only just inserting a delay, that our in one designer's hand is that what type of transistor it will use. And all of we know the transistor means that it's L by W ratio, that length and width. So here normally that in that standard cell based, one of these parameter, either length or width, is fixed. Only in user's hand is that only he can vary one thing, either length or width. So that here standard size transistor or double size transistor or quadruple size transistor, it is kept. Now based on its requirement, the chip designer will collect the appropriate one. So this is one example I am giving, and this is valid for that larger cells also. This is for the basic inverter, basic element, but it is valid for other cells also. That means in summary what we can tell, that it depends on that vendor, that normally we call that library vendor, or sometimes in real life it is called the phantom. That means you do not know that what is there in that black box, only the behavior is known and the test strategy is known. He may give you some test vectors and some cells, that means the behaviors are given. So here the inverter, the size of the inverter as well as the speed, that is given. Now based on that requirement, that designer will select that what type of library it will buy, or if it is already provided, then what it will select. Normally we include that libraries. Okay, again I'll discuss that ASIC cell libraries. Actually, our course, that VLSI design course nowadays, it concentrates that how we design that ASIC cell libraries. That this is the basic thing, that basic elements, inverter, the different gates, the different cells, and that three criteria I have told, that speed, power and area, that how to optimize that three things. So sometimes it is provided by some vendor, sometimes the designer can build its own library. So that's why that this semi-custom style or the standard cell library is nowadays is very important.
If the size is doubled, then delay is doubled.
Now size means what? Length or width? L by W ratio.
If it is doubled, means delay is doubled.
Not always that thing. That how you were, how that inverter you were designing, it depends on that. What type of design? We'll discuss that thing in details. The transistor. It is not as it is. Now, this is the layout of a typical standard cell. Normally, the power and the ground line, it okay. Just to see later when we'll do in practical cases, that time it will be more obvious. Normally, power and ground lines, or if you can think some rows and columns, the I/O pins that are that means that interfacing with outside world, that are normally they are made by columns, and these are some rows where the basic cells are placed. These are some rows, and the power lines as well as the ground lines, that parallelly it goes. Okay, and that NMOS normally they are kept, that ground lines nearer the ground lines and the PMOS are nearer the power lines. But why, that we will read later. So now we see only that type of standard cells are there. Now the characteristics of each cell, just I am giving some points, later we will discuss that inner thing. Each cell is designed with a fixed height. Why? Just now we have seen the picture, it is placed on a row and the height and width of the row is fixed. So to enable automated placement of the cells. Routing of inter-cell connections. Say if we design, the design style we use, the semi-custom design or standard cell based design, then what we are doing? Mainly we are collecting or we are taking the cells from our library. So the only thing the designer is doing, that is the interconnections. So the routing of inter-cell connections, for that purposes it is made, the height is made fixed. in one row the cells are placed. Now, a number of cells can be abated side by side to form rows. Normally, that cells that are placed side by side, they use the same power line and the same ground line, and that reduces the area. Now, the second point is that the power and ground line sometimes we call the rail. The neighboring cells shares share the same power and ground lines. The input output pins are normally located in the upper and lower boundaries, but there are other design styles also where that in the upper, lower as well as left and right, both the sides. Probably you have seen that microprocessor chips, some chips and memory chips are like that, where that all the connections are coming from the all four directions. That is also available. Normally, the design turnaround time is 8 weeks for that semi-custom design. Now, another important thing is the floor plan for standard cell design. What we are discussing, normally all the things nowadays are carried out by some CAD tools. But if you are the developer or you want to develop on your own CAD tools, then the issues you have to handle, that we are discussing as these introductory questions. But this floor plan for standard cell design. So, normally what we have seen in the picture, some rows and some columns are available. Now, between cell rows, here the picture we have seen that normally the cells are placed on row, and this between these cell rows that interconnections are there, because interconnection between cells just you think this is a row of cells are placed on this row, and some connections can be made between two neighboring cells. Then I use normally the columns for that connections. So, we can write that floor plan that between cells or cell rows are channels for intercell routing. Over the cell routing is also possible. Already we have discussed that thing, channelless or channel gate array. This is another important thing, that multiple cells are sharing a single row. So, when you are developing your own library, that heights of that cells must be same, otherwise you can't place that thing. So, that is why this floor planning and placement of cells is very important in that standard cell type of design style. I am giving one this type of, say, this is one picture. So, I'm taking one channel type of thing. So, these are standard cell row. So, some small cells I can put here. See here, the height of each cell is same, whereas the length can be of different type, because the size of the cells are different, but they are sharing one single row, but the height is the restriction. Height must be same, and these are the routing channels, this space between two rows. Now you see here the routing channel is shorter than the next one. Next one, the routing channel is larger. So now it is the designer's task, because they are taking, all the cells are available, these are ready-made cells, they are taking from the libraries, only these selecting these routing channels, that what will be the height of the channel, what will be the connections, that thing will, and it is done nowadays, it is done by some CAD tools, not by the designer. Sometimes at the back end, or actually we are discussing the floor plan, placement, routing, which are back end design, means the physical design automation. Sometimes the designer have to do this thing manually, because the CAD tools are again developed by some human being and they are not error free, or sometimes they cannot manage with this huge thing, then just by observing this thing, the designer has to do that thing manually. That means you have to give that some channel here, some connections there, some interconnections. So it is, that is why you have to know, the designer must know all these things, that why these connections will be there. Okay. Okay, later. Now the full custom design. The full custom design, normally we call that it is valid for analog design. Why I am discussing that thing? Say that for semi-custom designs, the cells are pre-designed or pre-verified, pre-tested, and just I am using that thing. For full custom, just based on my requirement, I am doing the design, the paper design, and just from scratch, or you can tell from starting from the transistor itself, you are doing the design. That's why it is called the full custom. Normally the speed is, we call approximate, that one designer, one expert designer can do 10 to 20 transistor he can design per day. So that's why it is very costly as well as it is very time consuming. So design turnaround time is highest or the for the full custom design. Still this is the most flexible one, because our main design criteria are the three, that speed, then minimum area, I am writing area, and then power. Then these all three things, how to handle these three things, that is on designer's hand. The entire mask is designed anew without any library. One type of example that where it is must, that is memory. The design of a memory, always it should be a full custom design, because if you think that memory is that repetitive blocks are there, so if you can optimize one, then actually you are replicating the blocks. So static or dynamic, you can tell that design of a memory cell static or dynamic must be a full custom one. But nowadays what we do, that full custom, standard cell, that means semi custom, or PLS, that means that programmable logic device type of thing, all we can mix. So if we do some comparison, among various design styles, then if it is FPGA, GATOR, this is standard cell, and this is full custom. Then we take cell size. Cell size here are fixed, because this is predefined. Here is also fixed. Here it is standard cell, only fixed height, because it is a row. But for full custom, it is totally variable. It is up to you, the designer. Then cell type. This is programmable. This is fixed, this is variable, this is also variable. Then cell placement. Cell placement, this is fixed, this is fixed, standard cell in row only, this is totally variable. Interconnections, interconnects, this is programmable. For FPGA this is programmable. This is variable, this is variable, this is variable. Then design time, for FPGA it is very fast, normally few hours, and that's why it is popular. Fast, this is medium, this is very slow, still always we need that full custom thing. Now we see
What's the difference between programmable and variable?
programmable means that designer can program that thing, the FPGA. From outside he can program that thing. And variable means, says just like I have shown that channel heights are variable. Now if we see some design, this is one single wafer, actually no design is there. I am keeping here. See, it is before fabrication. No, see this one is a if you see that thing, so here that actually basic cells are already there. This is one mask, you can tell. Ultimately this information, after all this simulation what we have discussed, that starting from the design flow, the starting from that problem specification to that up to layout, and these informations that you have to in some form, that mask informations you have to give. And this is one chip that in our advanced VLSI design lab we have designed based on that standard cell based design, and that here the technology file used is that taken from National Semiconductors Library we have used, and this is the chip is mainly for a sequence generator, and it is working in 250 megahertz. 250 megahertz. So here we use that library, that is a standard cell, but full custom is also you can use, full custom design also you can do. But for the, as we are mainly, this class is for digital design, so for digital design it is very unlikely that full custom is used. Mainly for analog we use that full custom, and digital normally we use that standard cell based design. But FPGA is parallelly is very popular, and for academics mainly for the cost and the speed. Here is not the speed of the design, that I am telling the design time, that is very popular.
Are there any reprogrammed PG segments?
FPGA is not reprogrammable. FPGA is not reprogrammable. Once it is fused, then it is once it is burnt, it is not cut. Reprogrammable, no, I think it's reprogrammable. So next day we start our course, that CMOS. Now this is overall some introductory portions we have covered. These are the common nowadays the different design styles. Okay. So mainly our lecture concentrates on the ASIC library design actually. Actually CMOS means nowadays that mainly CMOS is used for that cell design, and we will use that what will be the how we can come to that 3 points, that speed, power and area, how that can be optimized.